Alright, so for day 2 we're going to be finding limits algebraically. So we're going to look at the graph just to kind of review from day 1 and see how it's going to bring us into what we're going to do with day 2. So for this first part, we're looking at the graph of an absolute value function, and here is the absolute value function that we have. So for this first column, they want us to find f of a. So remember when you were looking at the graphs, f of a is where it's defined. So a, we're going to use the 0 here. So for f of 0, so if we go to our graph at 0, at the x value 0, we're looking at this y value of -2. Okay, so now I'm going to go ahead and find the limit, because that's what they asked for us to do here. So if I do the limit as x approaches 0 of f of x, okay, remember for the limit you have to check coming in from the left, that y value is -2. Coming in from the right, that y value is also -2. So the limit as x approaches 0 is -2, which is the same as here. Okay, for the next little example, it says the limit as x approaches 2 from the right. So we're just going to steal this 2, and I want to find f of 2. So if we look on our graph, the x value 2, that order pair is 2, -4, so y value there is -4. Okay, so now let's find this right-sided limit that they're asking us about. So the limit as x approaches 2 from the right. Okay, so here's 2. If you come in from the right, you're approaching that y value -4. If we would ask us for coming in from the left, you're still approaching -4. So the limit as x approaches 2 would just be -4. So this says when a function is defined, so define meaning that that point is filled in, okay, that y value is there, and continuous. So just to recap from pre-cal in your other math classes, continuous means there's no holes, there's no asymptotes, there's no jumps. This graph, if you run your finger across it, it keeps going forever. Okay, there's nothing there that makes it not discontinuous. So if it's defined and continuous at a point x equals a, then how can this limit be found analytically, or how can it be found algebraically? So what it says is provided that f of x is continuous at x equals a, then the limit as x approaches a of f of x is just that place where it's defined, f of a. Okay, these two examples up here showed us that. The limit as x approached 0 was -2 because it was continuous there, and that was the y value. The limit as x approaches 2 was -4 because the graph was continuous, and that was the y value there. So as long as the graph is continuous at x equals a, at the x value that you're looking at, then the limit is going to be the same thing as where it's defined. So that's going to help us with our algebraic part. So what we're going to do first, and what you're always going to try first, is direct substitution. Okay, direct substitution just means you're going to plug in the x value. You're always going to try this first. Okay, if it doesn't work, then we'll have techniques that we're going to use. But if you're doing this algebraically without a graph, then you're always going to try to do direct substitution. So our first example down here, the limit as x approaches 3 of this f of x here. To do direct substitution, you're just everywhere there's an x, you're going to plug in that 3 that we use. So 1/2 times 3 squared minus 2 times 3 plus 3. So this would be half of 9, so we could say 4.5 minus 6 plus 3. So that would be 7.5 minus 6, so we would end up with 1.5. Okay, so just to make yourself a note, what we did is we plugged in x equals 3. Okay, so that's it. So if we were to look at a graph here, because this graph right here, it's just a quadratic, that means it's always continuous, so this is going to work. Okay. Alright, and let's just make this is always continuous. Okay, so looking at part B, the limit as x approaches 3 of 5x plus 2 over 2x minus 3. So we're going to go ahead and just try to do direct substitution. So we're going to plug in that 3. So we're going to have 17 over 3. Okay, that was direct substitution. We just plugged in that 3. Now, this graph is not always continuous. The only place that it wouldn't be continuous is where this denominator would be equal to 0. So it's not continuous at x equals 3/2 because that would make that denominator 0. So as long as this number right here is not 3/2, then this will work. Okay, so that's why it works, because that one at 3/2 there. So when you're doing these direct substitution, you're not always going to have to tell where it's continuous, but if you can spot it out, it'll tell you if you're going to have to go to the next step. Alright, part C says the limit as x approaches 2 from the left. Now, doing the left or right, if it's going to be continuous, then it should work left or right, it should be the same answer. So we're just going to try direct substitution. So we're going to plug in that 2. So we're going to end up with 1 over 3, which works. The only way it's not going to work is if you end up with 0 in the denominator, and you'll know. So the only place that this would have not been continuous would have been if we would have had x equals -1, and then we wouldn't have been able to use this technique, because you can't have 0 in the denominator there. Alright, moving on to D. So we're going to plug in pi over 2. So those 2's can cancel, and we'll just have sine of pi. So this is why I say it's important to know your unit circle, because these problems are just going to be thrown in. Like the topic's not going to be about the unit circle, you just have to know. So get to the point where you can just draw yourself a little picture. We know pi is over here, and that ordered pair is -1, 0. And because sine is the y value, then the answer to that is 0. So that's how you use direct substitution for that. And then if we look at part E, once again we have some theta values, so we're going to plug in 2 pi over 3. Okay, so we do need our unit circle for this. So 2 pi over 3, we know that's less than 1, so it has to be in the top half. And 2 pi over 3 is that first little link right here. We know they always have 2 in the denominators, and in the top half, 1 start with the x's and ends with 3. Because we move left 1, that's going to be a -1/2. Okay, so cosine is your x value, so it's going to be -1 or -1/2 in the numerator over 2 pi over 3. And then because we have a fraction over a fraction, we're going to do same change flip. Nothing cancels here, so we'll have -3 in the numerator over 4 pi. Looks a little strange, but it's perfectly fine to leave your answer like that. And then for this last one, part F, it's working with logs. Still same thing, we're going to try to do direct substitution. So log base 8 of 11 minus 9. So that's log base 8 of 2. Now doing this without your calculator, if you want to do this, you can set this equal to a variable. So I'm just going to set it equal to x. It's in log form, we can put it in exponential form. So the base is 8, exponent is x, and that's equal to 2. Now I know this is 2 to the first power. So I want to rewrite 8 as a base of 2. Well, we know 2 to the third is the same thing as 8. And now because my bases are both 2, you can set their exponents equal. So x is going to give us 1/3, and that will be the answer to that part. Okay, so direct substitution, you're going to always, if we're doing these algebraic, if we're doing limits algebraically, you're always going to try direct substitution first. So all that means is you take the x value and you plug it in. As long as the graph is continuous at that point, it will work. And what I say by means it works, you get a number that's actually a real number, versus getting a 0 in the denominator, which we will look at when we look at the next part. So direct substitution is what you're always going to try first.